All right. So good morning. Okay, so today I've got exams to pass out to you, and we'll go over the exam solutions. The average was about a 78. I think it was 78.5 actually. So we could round it up to 79 maybe. So it was okay, and I think that for the most part, people did fairly well. So I'm just going to take a minute to pass these back out, and I guess maybe some people will show up late and whatnot. But I'm just going to go ahead and read off the names. So Francesca Hunt, Alexander McDonald, Aaron Walsh, Lauren, Sydney, Abby Mitchell, Carolyn, All right. Yes, thank you. And so if for anybody who didn't get theirs today, you can always I'll have it in class next time. So no problem. And thank you for the email, Tucker. All right. So today I just plan to go through the solutions to kind of have an idea of what's going on, where you made a mistake, and you can also use this as a time to double check that you feel like it was fair or reasonable in terms of the grade I assigned. What I was trying to do was essentially, as always, my aim is to grade you based on what you learned, right? Or at least based on what I could tell that you learned, right? Hopefully you learned more than you learned everything. But essentially my grading scheme then is if you make like a very minor mistake, you flipped a negative sign, you forgot or you misplaced a digit or something, that's about 10 points off or 10% per mistake on a given problem. So if the problem is 10 points and you made a little mistake, it would be like -1. If it was a more major mistake where I could tell you got a concept wrong, you thought you needed to use a batch reactor, but really you needed a CSTR, that was about 25% off per kind of major mistake like that. So, and that's sort of rough, depends on how I arrange the points. And so, for example, on problem 1, I went ahead and counted the part A as 5 points, B as 10 points, and C as 5 points. So it kind of depended a little bit on how much points were available on a given problem. But that's sort of my aim. So if you got a problem absolutely entirely every part of it wrong, but you gave it a nice full-fledged effort, you probably get like 30% of the credit, maybe 20% if really I saw everything was wrong. But you still get some credit for that. So even if you're feeling lost, do give it a shot and show me what you have gleaned. Okay, so problem 1, we had a conventional wastewater treatment plant. Treats a flow of 0.44 cubic meters per second. Primary treatment step consists of a grit removal chamber and its clarifier and has a hydraulic residence time of 15 minutes. This process removes BOD based on a physical process which can be described with a rate constant of 0.05 milligrams per liter per second. And it says answer the following questions about the system. So from the start here, you'll notice that we haven't really talked much about grit chambers or, yes, we have a clarifier, so it's some sort of sedimentation, but we really haven't even gotten into the wastewater. So none of this should be, none of the context here should be something that you are worried about in a sense of applying the technical detail. You need the technical detail to understand how to get the rate constant for a flocculation reaction, right? You need to know that K, the formula for the K, all of that. So this is just basically we have some process that you should know that we haven't learned directly about, and we know we have some residence time, we have a flow rate, and some sort of reaction. That's kind of what we know. And we have, okay, of course, this flow going through. And if you think about what's going on with a grit removal chamber, it's just water flowing through something, removing stuff, right? And then the clarifier as well, it's just removing stuff. And so when I tell you it's removes based on kind of a physical process, can be described with this rate constant, well, first thing you ought to do is look at that rate constant and say, oh, we have some rate constant. It's a removal, so it's going to be a decay reaction, some sort. Then we look at the units to determine the reaction order, and we notice this is in milligrams per liter per second. So that's a concentration per time. That means it's going to be first order, or zero order, excuse me. Okay, so I suppose you could think of this system and say, well, I don't know if it's plug flow or a batch reactor. And to be fair, I didn't really give you much context there for that. But it's just water flowing through a couple steps. It's not really, I guess probably the best way to treat it would be as a CSTR, but in fact, since it's zero order, it might not even matter. So I think the math might work out either way. But I would think of this as a CSTR with at steady state we have QC naught of whatever this stuff that we're removing minus QC minus our VK, and we could do C to the 0 power for a zero order, or we could just leave it off. Okay, so that would be kind of our mass balance setup to solve something, but that'll be part B here. Actually, I'm ahead of myself. Part A is just asking what's the effective volume for the treatment system. So we were given a theta. We want volume, we were given a theta, and we were given a flow, right? So we can get the volume from those two. So the flow rate was 0.44 cubic meters per second. And the theta was 15 minutes. We could change that into seconds. We could say that's 900 seconds. And so if we say our theta is V over Q, then that means our volume should be theta times Q. Right. So then our volume will come out to be 396 cubic meters. Okay. Does that part make sense? Good there. Okay. All right, so then part B says, here's where we'll need that mass balance. If the influent raw sewage has a BOD of 450 milligrams BOD per liter, what would be the BOD in the primary effluent? So here's where we would need the mass balance. So we'll say that's 0 QC coming in minus QC going out minus the VK. This will be the CSTR case. Maybe we'll solve it just for fun as if we treat it like a plug flow in a moment. But for assuming it's a CSTR, this is what we would do. We solve for C in this case. We need C times Q. It's going to be QC naught minus VK. Solve for C, and we get C naught minus essentially theta, so that's V over Q times K. So that'll be our mass balance. It's very simple because it's a zero order. Pretty straightforward in that sense. We had some initial concentration given. That's the 450. So that'll be 450 minus the 15 minutes, but we should probably put that into seconds because our K was 0.05 milligrams per liter per second. So if we want an answer in milligrams per liter, we should use the 900 seconds here. You can go ahead and note that's milligrams per liter. So we 900 seconds times 0.05 milligrams per liter per second. So writing out the units here helps reassure us that, first of all, we don't need to convert that liters to cubic meters because we want an answer in milligrams per liter. And we recognize that we have everything in seconds properly. So that gives us a C value of 405 milligrams per liter of this BOD stuff. Okay, does that make sense? Okay, so let's see what happens. I had not thought about this while I was grading, but if you had assumed it was a plug flow reactor instead, our mass balance would look like this. And I think that I would have a little bit of sympathy if you did it this way, now that I'm thinking about it, because I really didn't give much information. But given that things are just like a grit chamber removal system is just going to be like kind of a screen. So it's just water flowing through it. And it's like the zero order process is just, we're taking some amount of it out. It's just like, we're just taking, a steady amount out constantly. So it doesn't strike me like a plug flow reactor. But let's say you did that. You would be V dc dt equals we could treat it, so if we are treating it as if it's essentially a batch reactor going through with this rate, be that volume times, and this would be a negative, be decreasing over time, V times K times C to the 0 power. So we would have just simply that. So C minus C naught, once we integrate, negative KT, where T is theta. Oops. So that brings us back to the same equation, right? Because it's a zero order. It ultimately did not matter. So either way you go, as long as you recognize that it was a zero order reaction, then that should have been okay. All right, so then the part C says, what is the overall BOD removal efficiency? And so this is, I guess we didn't really learn this directly per se, but if you're talking about removal efficiency and I'm asking in percentage, that's going to be kind of what you started with minus what was removed. So that's what's remaining divided by what you started with, right? So it's removal efficiency would be, well, I guess we should say removed, right? The stuff removed over the total times 100%. So the fraction removed would be the removal efficiency. So that would be C naught minus C will give us the portion that was removed divided by C naught times 100%. Okay, so that'll be essentially 45 over 450 times 100%. And we can see that's going to give us essentially 10% was removed. Any questions, issues? Okay, so problem 2, we had jar tests for flocculation. And I think this is one problem that what's this one? I don't think anybody got part D correct, but I think in general people did okay on the problem. So part A says let me just back. We have jar tests to measure the effectiveness of coagulation at a lap scale. We're going to consider a 4-liter jar with a submerged stir to answer the following questions, 20 degrees Celsius. We have a stir powered by a motor that's giving 0.07 milliwatts to the jar. And so the question is, what is the mixing intensity? This is coming from the equation where we have the square root of the power in watts divided by the volume of whatever basin or reactor we're using times the dynamic viscosity of water. So the dynamic viscosity at 20 degrees Celsius was 1.02 times 10 to the minus third kilograms per meter second. The volume of this reactor is 4 liters, but we need this to be in meters because all the other units are in meters. So if you didn't do that, that would be a problem. So that's going to be 0.004 cubic meters because there's 1,000 liters per cubic meter. Then our power needs to be in watts. So the power then is going to be, essentially, we were given this in milliwatts. So it's 0.07 times 10 to the minus third. Or you could write that as 7 times 10 to the minus fifth if you wanted to. But basically, we just need to make sure we get the right digits here. So already had 1 0. I'm going to add 3 more. Put it there. Call it watts. And then we can go from there. Okay, so with that, then if you put all that in, G should be equal to 4.14 per second. Okay, so usually if there was some issue here, it was probably a failure to convert the 4 liters into cubic meters, or perhaps miscalculating the power in watts or misapplying it, or something like that. So there was some mistakes here, very trivial in nature. So I'm not too concerned about it, but do yourself a favor and write your units out as you put them in. Okay, so then part B was kind of a little bit more challenging, a little more involved. Here we have these particles have an initial diameter, or initial amount of particles, 1.5 times 10 to the 7th particles in the jar. They are 40 micrometers in diameter. Question is, how many particles per liter will be in solution after 30 minutes of stirring if the particles are completely destabilized? So we've got this flocculation reaction. Particles are completely destabilized. So we know that alpha is 1. That goes into our K equation that we have here. We know we need these different components, so we're going to need, we already solved for G. If you got that wrong, I tried to recognize if you got the rest of the problem correctly, and if so, not take many or much, if any, points off, if so. But I was also checking a few other things. So that was, we already got G from before. Just go ahead and write that up again. Specifically, I would check to make sure you got the omega correct, which the equation here is essentially the pi dp cubed times the initial concentration of particles divided by 6. But here, N naught was a little bit trickier than I think most recognize. So N naught should have been this 1.5 times 10 to the 7th particles in the jar, but it's a 4-liter jar. So we need to divide that by 4, and then not only that, but we also need to make sure we put that in cubic meters units instead of leaving it in liters, because our n naught has to be put into meters, or excuse me, the dp has to be put into meters. Maybe we could put this in some number per microliter, cubic micrometers, and leave a dp in micrometers. That would be okay. It would be awkward, but okay. Or it would feel awkward to me anyway. So what we'd have to do here is 1.5 times 10 to the 7th particles. And that's in the 4-liter vessel. So that gives us a 3.75 times 10, I think still to the 7th. Let's see, that should be to the 6th, right? Particles per liter. I don't actually have it written, but I think that's it. If you have that, please double check me there. Okay, then this ohm here, this mega, excuse me, pi dp cubed. dp has to be 40 micrometers, but convert that to meters with the cube exchange there. And then the n naught also we need to put into liters. We could also write that as 3.75 times 10 to the 9th particles per cubic meter. So we put all that in, and we should get a value of 1.26 times 10 to the minus 4th for our value there. And that is unitless. Okay, so if you didn't get that part right, you would have had some points off because okay, so anyway, that was the tricky bit, the 4 liters. Otherwise, I think most people had the right idea here because you recognize it's in a jar. So the equation we're going to use is essentially it's a batch reactor. And it's a first order decay. So it's going to end up looking like n equals n naught times e to the minus kt, and that will be our tool to get n at time 30 minutes, would be this n naught, which we solved for, times e to the minus k, which all these things put together we can solve for a k. So is the other thing I checked. If you had gotten the omega right, then and the g correct, then you should also get this part correct. It was 6.63 times 10 to the minus 4 per second. So we could put that in here as k, and then the time had to be in minutes, or seconds, I mean, because that k is in seconds. So that 30 minutes times 60 would be 1800 seconds. So get all that, and you would get an N30 value of 1.14 times 10 to the 6 particles. Should have been the answer. Okay, and I think 1 or 2 of you got all of that correct, but it was quite an involved problem in that sense. So I think most people lost at least a couple points. Part C then said, what is the average number of singlet particles in an aggregate after 30 minutes? So here, I was really looking for you to approach the problem correctly, because at this point I knew most of you had not gotten part B fully correctly, so that wasn't really bothering me, so long as you took an approach to say, oh, okay, this n naught over n30 was what I was asking for. So if you solve it based on taking a look at how many initial ones per final one, that's this ratio. That's what you needed to do. And even if you got some of the problem incorrect, you could have gotten a reasonable number. Some of the mistakes that were made it so that the K was, I think, very small, so there wasn't much of a change in the number, so it was very close to 1 for some of your answers. If you had gotten everything correct, this would come out to be pretty much 3.3 particles. And as the average number of single particles, I think that's okay. Just put a fraction there. On average, there was 3.3 individual particles, but you could also round that, I suppose, to 1, or to 3, and that would be okay. So that was really all I was looking for, was you to recognize that that's how we need to solve the problem, is that initial over final to give me the answer there. Okay, so for part D, question is, what would be the sedimentation velocity if the resulting aggregates, or of the resulting aggregates, after the jar test runs for 30 minutes, if the particle density is 1.33 grams per liter. Okay, so maybe I was being a little bit overly ambitious at this point to add on a bit of sedimentation to this flocculation problem to kind of connect all the dots. I think if I go back and reuse this question, what I'll probably do is give you a new value just as an example. Assuming it was 3 particles, 3 of the initial particles in each aggregate, right? Go from there. So essentially what I'm looking for is a VS, but of the new particles. And here's where I think everybody made a mistake. I was looking for the VS of the new, whereas pretty much everybody gave me VS for the old. So basically, I think if you did everything correctly, but except without recognizing that you need to solve for the new diameter, then I took off 2 points. So the VS for the old, of course, we need to use the equation for sedimentation velocity. It's G, so 9.8, times the rho of the particle, which if you convert, you need to make sure to do that correctly. This should be 1330 kilograms per cubic meter, because our water is also going to be in kilograms per cubic meter. That was at 20 degrees Celsius, that's 998.2. This times our diameter of the particle. So again, if we're solving for the old one, which we didn't really need to do, but everybody did, that would be 40 times 10 to the minus 6 meters, all that squared, then divided by 18 times our dynamic viscosity water, which again was 1.02 times 10 to the minus third. Okay, so if you did that, I don't remember what exactly the solution was, but that was like the closest incorrect answer, I suppose, if you did all that properly. So I was checking to see, basically, had you converted the units properly, to see if you did that part correct. If you did, it appeared that you did all those pieces correct. Then I think I only took off 2. But really, the bulk of this question was centered on that example problem we did, where we had to find the new diameter from the aggregate, right? So we had done it in class. We had, if dP is 40 micrometers for the old one, or for the initial, then a dP new was the question, and we'd have to put that into our equation. And that's going to bring us back to the volume, because we can compare the volume of the initial particle times that 3.3. And granted, many of your answers for the n naught over n, you got 1 because of the way you solved it. But I was really looking to see if you had calculated a new one. So if you did write something that, and you felt like you justified that the reason you used 40 was because it was a 1-to-1 ratio, you can bring that to me and show it to me, and maybe I'll give you some points back. But basically, I was looking to see if you had written something about solving for a new diameter, because you needed to do that using the information, right? They formed these larger particles, So the volume of an initial particle times that 3.3 or times the n naught over n should be equal to the volume of the aggregate. So that's the way we can compare, and we can set that up and say, let's say, I'm going to flip these backwards because that's the way I have it in my notes. Pi times the diameter of an aggregate cubed over 6 is going to be equal to 3.3 times pi over 6 times the diameter of the initial particle cubed. Okay, so then we can solve for the diameter of the new, or the aggregate, by taking the cubed root of dp initial cubed times 3.3. So that would then give us a diameter of the aggregate equal to something larger than what we started with. In this case, that was 59.5 micrometers. And so the VS new was 6.28 times 10 to the minus 4th meters per second. And just as a side note, had you done it, had you solved it for the old particles, the initial particles, you should get something that is similar to but smaller than this, right? It won't be settling as fast, but it'll be nearly the same order, 10 to the minus 5th or 4th. Okay, does that make sense? Good on that? Okay. All right, so then problem 3 says, in order to keep 3 Olympic swimming pools clean, several granular filtration cartridge units are used. Each unit is cylindrical with 1.25 meters in diameter and 1.5 meters height. The pool contains 2.5 million liters of water. Each pool, that is. The filters must treat enough water such that the hydraulic residence time is 1 day for each pool. So basically, we're cycling one full volume of the pool every day. And that water is actually recirculating back in. Okay, so that means we're not having like a net flow anywhere. It's just irrelevant for the problem, really. Just kind of context there. The filters are pressurized and operate at a high rate of 15 meters per hour during filtration and 25 meters per hour during backwashing. They automatically backwash and rinse after 24 hours of filtration time, taking 15 minutes for each process. So part A says, what is the effective loading rate of the filters? Answer in meters per hour. So this is asking us to solve for our effective loading rate. And we have an equation for that. That would be the volume produced during filtration minus the volume used during backwash minus the volume used for rinse. All that divided by the area of a filter times the total cycle time. Okay, so the area of the filter would be kind of the first question I'll answer here. That's going to be, we have 1.25 meters in diameter. So this is going to be the area of a circle. So it's pi r squared. And I'm going to say that's diameter over 2 squared. So that's going to be, when you solve that, should have been 1.227 square meters. I know that some of you got that wrong, so just make sure you're comfortable getting kind of the essentials from geometry. Pi r squared should be the area of a circle, and you have to make sure to square that diameter over 2 or solve it outright before you do that, because an easy mistake to make would be diameter squared over 2. That would be incorrect, right? Because you have to square that divided by 2. Okay, so we've got the area there. The total cycle time, we said it stops after 24 hours of filtration. So whereas we had done a problem with 24-hour cycle time, this problem says specifically that it stops after 24 hours of filtration time. So we know that before we do anything else, we could say the time of filtration is 24 hours. That means this total cycle time is 24 hours plus however long it takes to do the filtration and mixing, or rinsing, excuse me, which is 15 minutes for each, or half an hour total. Right now, I'm just leaving it in hours. We could easily convert all this. Should be time for the rinsing would be a quarter of an hour, right? 15 minutes. My mind's like, okay, let's write 0.15. Okay, so of course we can change all those from hours, but I think everything's in hours, and that might just be might be the most convenient thing anyway. Okay, so we have all of that. Then we will solve for our volumes used for rinsing, backwashing, and achieved during filtration. Essentially in the same manner. We have the area of the filter times that loading rate times the amount of time for that process. AF. During the rinsing, we're loading at the same rate as we would under normal operation. And during backwashing, we have a special V for backwash. And again, that lowercase loading rate V. And so when we solve these with those units in place, we should get 441.8 cubic meters for the filtration. Should get 4.6 cubic meters for the rinsing, and 7.67 cubic meters for the backwash. So then we can put all those into our effective loading rate equation and get an answer, and we should expect this answer to be a little bit below our loading rate. So our loading rate was 15 meters per hour, so we expect this to be lower than 15, and if it was not, we would have some concern. So 14.29 meters per hour is lower, but not by too much, so that makes some good sense there, gives us a bit of confidence. So 14.29 was the answer I was looking for that, meters per hour. Part B said, how many filtration units are required to keep the pools clean? This is coming from the information provided about kind of how big the pools were, how often we are filtering, like what kind of a flow rate do we need. And so essentially what I was looking for you to do is decipher that we need some sort of a flow rate. And essentially this is going to be, we said we need to keep them clean, we had to filter each of the pool's volumes once per day. So this is going to be 3 pools per 1 day is the crude way to put it, right? So that's the flow rate of water that we need to meet through these filters. And so that's going to be, of course, you don't have to write 3 pools, but basically you'd have to get the volume, because that's volume per time, and that's going to be 3 times the volume of the pool, which was given as 2.5 million liters. So 3 times 2.5 times 10 to the 6 liters in 24 hours, you could put it. So that's going to be 7.5 times 10 to the 6 liters divided by that 1 day. So once you solve that, it should come out to be 312.5 cubic meters, because we can convert from liters to cubic meters. So 312.5 cubic meters every hour. So with that, then we can solve for the number of filters we need. And essentially what we're going to do is we're going to say we have to meet that flow with some number of filters, given that they're effectively operating at the answer we got in part A, which was about 14.3 meters per hour loading rate. So a couple different ways you could write this up. You could say that flow rate is going to be equal to the number of filters times the area of one filter. You could also write those two combined and say the total filtration area. And you know the total filtration area is going to be the number of filters times the area of one, right? So it doesn't really matter too much how you express that, but it should be intuitive that those two are the same thing essentially. And this times the effective loading rate, because this will give us, again, meters per hour here times meters squared here. This is just some number. And so combining those two, that'll give us cubic meters per hour, right? So that's what we would look for to make sure we have the correct units. So doing this, we could then solve for the number of filters as Q divided by the area of one filter times that effective loading rate. And when we put those in, assuming we have everything in meters and hours, we should get an answer of 17.8, and we have to round that up to the nearest next filter, so that'll be 18 filters. Okay. Any questions, issues?
Are we supposed to just assume that you meant all of the pools just because pools is plural now? Because I just saw.
Yes. Good call that it was not super clear, I suppose, but yes, that plural is I probably shouldn't rely on just one letter to inform your entire problem. So if you felt that's unfair, you can talk to me about the grade after. And fair enough. That's yes, but it literally is. If I accidentally did a typo there and just had to keep the pool clean, then your answer would probably be correct, right? So perhaps I should only count off 1 point because it's 10. A small, such a small error to make, right? Okay, so hopefully though I would have seen that you did most of it correct, and that would be the one thing. All right, so then part C says what is the filtration filter efficiency? So this is talking about on a water basis. So this is going to be that equation for nu here, which is essentially the volume of the water basis. So it's the volume filtered minus the volume used for backwashing and wasted from the rinsing divided by the total volume filtered. And in the sense of the pool operation, since most of the stuff's getting recirculated, this would actually give us what percentage of the water do we have to replace every day, essentially. So that's actually probably a pretty meaningful thing to know for a pool operator, so they know, okay, how much time do they need to put the hose or however they're filling their water. How much do they have to add? Of course, they'd probably add some water losses from evaporation and some other stuff. And I doubt that a pool operator is going to be really that technical. But if you were to design a system up front and want to predict the costs and all of that, maybe you would do something like this. Okay, so we had all the volumes already solved for. So given that, we should be able to just go ahead and solve. That should be 0.972. And you should be able to get pretty close, even if you did, let's say, make a mistake on the area of the filter. That mistake would be pretty consistent throughout, so that there's a good chance you've got this pretty close to correct. That was 2 there, by the way. Even if there were some mistakes. Okay, so problem 4 said a membrane module comprised of several tubular membranes has an effective surface area of 12 square meters. The membrane system is operated in cross flow under a constant flux regime to yield 1,500 liters per hour of water. The treated water is 20 degrees Celsius. And so part A says each tubular membrane is 2 meters long and operated in an outside-in regime. If the tubes have an outer diameter of 2.2 centimeters, how many tubes does each unit contain? And I ask you to round up to the next whole number. Okay, so we're given a lot of information up front, and then we're asked about how many of these tubes do we have? And essentially, this part of the problem is, again, just a geometry problem disguised as a water treatment problem. So we have these tubes. We know that in the entire unit there are several tubes. Not sure how many. Maybe it looks something like this. So we have this unit, got some number of tubes in it, and each of these tubes are operated, they'll have some sort of thickness to them, and they're operated outside in, so water is going from the outside of these tubes into the middle and then coming out this way or going the other way. Mason says online that he and Caroline saw one of these membranes at WEFTEC yesterday, so that's fun. Did that help kind of make more sense of what these are talking about?
Yeah, it's like make everything unreal. It's kind of funny.
That's awesome.
Like, oh my gosh, I'm learning about this.
That's cool. How big were they?
Not big.
Just kind of like a unit like this,
It's
or
like a little model.
okay,
It just had like all of the tubes in one big tube looking thing.
cool. Anybody else going to WEFTEC? As I'm hearing about it and stuff, I was like, sounds like that'd be interesting. I'd like to go, but especially since I'm not going there to present something that's like for me to register to attend everything, it'd be like almost $1,000. So yeah, it'd be a lot, and then I couldn't be here for you. Of course, I could go on Monday, Wednesday, and such. Anyhow, okay, so this problem is talking about that, really dealing with that outer diameter. That's going to be our separation. And so what we're looking for to answer this problem is, okay, how many of these tubes are required to meet a total surface area, say area total, of 12 square meters. So we need to know that surface area for one tube, and that's going to be this length. So the surface area here is going to be essentially the length times the circumference of the thing, right? So we have a length, and then we have a diameter. It's 2.2 centimeters. Length was 2 meters. So the area here should be length times 2 pi r, or pi times diameter here. So that's going to be 2 meters times 0.022 meters. And keep in mind this is centimeters, so that's 1/100th of a meter. This is not millimeters. I think there was probably a couple of conversion errors there, but that should be 0.022 meters times 2 meters. That's going to give us, of course we have to multiply by pi as well. And that should give us an area for one tube to be 0.138 square meters. So then the area of the tube then, or so the the total number of tubes is going to be a lot like what we were looking at a minute ago with the previous problem. We're just looking to find some total area here. We actually don't need all the flux information and all that yet. We're just saying the number of tubes is going to be equal to the area total divided by the area of one tube. Right. So that's going to be 12 square meters divided by 0.138 square meters. That's going to give us 86.8. So that means 87 tubes. Okay, so if you were overthinking it, then you were trying to apply your flux or some other aspect, when really we just needed to recognize that we have some total surface area, and each of these tubes is going to satisfy part of that. So if we did put 87 tubes, each with about 2.2 centimeters, we're looking at a pretty big unit, and tubes that are actually fairly small, not hollow fiber kind of millimeters small, but not very large. Okay, so then part B says if the membrane resistance is 7.85 times 10 to the 12th per meter, what is the operational pressure that must be applied across the membrane to achieve a flow that was described earlier, that 1500 liters per hour? And I asked for an answer in kilopascals. So here we're looking at our equation. We know we have an equation for resistance equal to the transmembrane pressure. That's the pressure we're talking about in pascals, divided by the flux times our viscosity. Okay, so we know the viscosity. We've been using the same temperature for the exam. This is at 20 degrees Celsius. This was 1.02, excuse me, 002. I may have a few minutes ago I wrote 0.02, so I might have one or the other of these slightly off. You guys didn't catch me. Hopefully I just wrote it wrong and did the calculations correctly in Excel. But please let me know if you see that I've done it wrong. Should be 002. So double check that I have not incorrectly taken points if that was. I think that would be small enough of a mistake that it wouldn't really register. So, but do double check me on that, and I'll try to go back and make sure that the answers I gave are correct. Okay, so we have the mu there. The flux is going to be another thing we need to solve, and the flux is going to be the total flow over the area that we are dealing with. So that's going to be for the flux. We can write that as 1500 meters per hour divided by 12 square meters. With that, we should also have, we know our R, so really what we want to do is solve for transmembrane pressure to be R times the flux times the mu. And we'll need that in seconds also, because our mu is in seconds. So we would want this in meters per second. I don't have that written for you. But when we solve, put it all together, this transmembrane pressure should be 273.1 kilopascals as our answer. That makes sense? Issues? Okay. All right, then part C says what pressure must be applied must be applied to keep the flux constant if the fouling doubles the membrane resistance. Okay, so we need the same flux, so that didn't change in the problem. Essentially, the only thing that changed was R. So when we solve for TMP as R times our flux times mu, well, mu is not going to change. That's a feature of the water and the temperature, so that's going to remain constant. J is going to remain constant, so if we look at what happens, let's say question mark number of TMPs, the number of the pressure that we had before equals 2R J times U, then that question mark is 2, right? So we just have 2 times the pressure. 2 times the pressure equals 2 times the R times J times mu. So really this, without doing any of the actual calculations, of course you could just go back in your calculator or whatever, put the numbers in again and get it. But really all you have to do is double the 273 to get 546.2 kilopascals. Okay. All right. Any other questions, issues? Well, that's all I had for you today. I will have the exams next time for anybody who didn't get them. I guess next time will be a week from today because we've got fall break. And we will resume with our disinfection, probably talk about some ultraviolet stuff. And I'll spend a few minutes here if anybody's got questions. I'm going to go back quickly through, I'll stop recording, but I'll go back through and double check the numbers. And I'll correct the PowerPoint if there are any corrections I need to make. So, all right, with that, have a great week and enjoy your fall break.